So this talk, which is on the knot theory side about multi-virtual knots and links, is going to dwell for quite a while about coloring problem because I wanted to show how this particular way of thinking about more than one virtual crossing arose in my thought out of thinking about coloring things and Penrose evaluations and things like that. So I'm going to start with the three coloring problem, the four coloring problem, depending on whether you want to color the edges of a graph, as State did, or the regions of the graph, as other people did before him. So the problem of three coloring the edges of a cubic graph or trivalent graph is that you want to have three distinct colors, call them A, B, and C, or call them red, blue, and green, or 1, 2, and 3, and I think I probably shift back and forth among those, all distinct colors at a vertex. So you're looking at a three-colored cubic graph right there. And the four-color theorem turns out to be equivalent to coloring planar cubic graphs that are one connected in the sense that there is no single edge which, if you were to remove it, would disconnect the graph in the plane. Now, I immediately digress. Um, I digress because this is related to some other talks that happened here. Um, Hassler-Whitney, around 1920, proved that the four-color theorem is equivalent in terms of coloring cubic graphs to coloring matched trees in the sense of the diagram that I have here in the middle of the slide. You're looking at a cubic graph, certainly, and the lower half of it is a tree, and the upper half of it is a tree, and the roots of the trees are connected to one another like this. Um, and Hassler-Whitney proved that if you prove that you can color all such graphs, then you've proved the four-color theorem. So go off and do that, and everyone will be very interested in your proof. Um, and then there are ways to reformulate this. Oh, now the reason I mention it before I start saying anything more about it is that in other talks in this conference, been pointed out that a pair of trees like that, not necessarily connected like that, corresponds to an element of the Thompson group. So the Thompson group, it's possible to ask, can you color this element of the Thompson group? And four-color theorem says, yes, you can. Um, and maybe the structure of the Thompson group as a whole, which is the structure of these graphs, will be a key to some eventual other proof of the four-color theorem. More work needed there. Now, as for what you can do with the trees, that's also interesting. If you have a tree like A, B, C, and D and B, and D and E here in the tree going down, then you can think of some labeling by some system by which you could multiply, and then this would be AB, this would be AB here coming out, and then AB times C, and and then you would have AB times C here, and over here you have D times E, so you'd have D times E here, and then you multiplied them together, and that's the name of the coloring on this outgoing line. Similarly, the upper tree gives you an associated product, and so you can ask in the abstract um, to see that coloring such a tree with the roots connected that way um, would be the same as solving some equation about non-associative products, which suggests that you ought to be in some Lie algebra trying to do that. And there is an appropriate Lie algebra, and that's the cross-product algebra in three space, the Lie algebra of SO3. And it turns out that the four-color theorem, by means of this kind of translation, is equivalent to saying that you can solve all such equations, non-associative equations, using only I, J, and K in the cross-product algebra. And those are the three colors from that point of view. So that's an interesting digression. We'll leave the digression and go back to the ground of coloring now. So what is the relationship between coloring faces and coloring edges? Well, the relationship is the so-called Klein foregroup. That is, you can have four colors, W, A, B, and C, capitalized, and the product of any two of the W is the identity element, and the product of any two other elements is equal to the third, and the square of any element is equal to the identity. That's the Klein foregroup, Z2, direct sum Z2. And you use the group multiplication to go between edge coloring and face coloring. If you have two colors on the faces, like W and B here, then the edge between them is their product, which I've written in small. Here's C and B, and the product is A in small. And you can go backward and forward between face coloring and edge coloring in that way, and that idea is, I think, surely due to Tate. So the four-color theorem and the edge three-color theorem are the same. Another relationship which is worth mentioning for what we're about to do is the fact that if you have a colored graph, and here I have one, you can choose one of the colors, and then you get a collection of edges, all disjoint from one another, that take up all the vertices in the graph. That's called a perfect matching. So a perfect matching occurs whenever you have a coloring. And furthermore, this perfect matching is even in the sense that if you were to remove the matching edges, in this case the edges labeled C, and look at the cycles in the remainder, they're all even cycles. And they are all even cycles in the case of a coloring because they are alternately labeled by the other two colors, A, B, A, B, A, B, A, B, as you go all the way around the one cycle in this example. So you get an even perfect matching. And searching for a coloring of a graph is the same as searching for an even perfect matching. It's not hard and goes back to Peterson that you can find perfect matchings for trivalent graphs. And the proof of that is not entirely trivial, but it's within one page on the Wikipedia. To prove the four-color theorem is not within one page of anybody at the moment. Okay, so perfect matchings come in. Um, and then another uh, coloring visualization is useful. And in this one, I'm coloring by red and blue, and I factor purple, the remaining color, into red times blue, visually factor it. So here I'm drawing a picture of this coloring where A is red and B is blue and C is purple, red times blue. And then what I do is I draw alternating loops going red, purple, red, purple, red, purple until they come back to themselves, and blue, purple, blue, purple, blue, purple until they come back to themselves, and regard those alternating loops as blue and red. And of course, when it goes through purple, it may be going through as blue or it may be going through as red. And you factor the coloring into a collection of Jordan curves in the plane which meet along um, some intervals, and those are the edges in the graph that are doubly colored. And those intervals may cross each other. I mean, the color curves may cross each other. You may have blue coming in, sharing a bit with red, and then going off on the other side of red, or it may come in, share a bit with red, and come off at the same side. So this one is going off on the same side, this one crossed blue, and so on. And I'll call that a formation. The term formation is due to G. Spencer Brown. And as you see, it's a variation of the Tate coloring that lets you think of the coloring as a combination of red and blue curves. It's worth making a further comment about this. Um, this is something that you could draw in the plane, just having drawn it. I mean, you could take a colored pencil and draw some blue curves disjoint from one another, and then take a red pencil and draw some red curves which shared some edges with the blue curves, and then after you'd made your drawing, you can step back from it, and you can say, I have a colored graph, namely the graph that's associated with this, where you have edges for single red intervals, edges for single blue intervals, and edges for doubly colored intervals. So a formation gives rise to a graph, and a graph can give rise to many formations depending on how it's colored. So the four color theorem says that when you make up formations, of which you can infinitely to your heart's content, you will end up covering all of the one connected cubic graphs. So lots of evidence for colored graphs because you don't have to try to figure out how to color them from the formation point of view. You just produce them. Now we get to the Penrose formula. In his amazing paper on applications of negative dimensional tensors, which comes from originally from his PhD thesis in the 1950s, Roger Penrose shows this formula, which allows you to count the number of colorings in a planar cubic graph. It's a skein relation, as you see. And what you do is you go up to any edge in the graph and you smooth it or you leave it as a crossover. I draw a virtual crossing to remind us that these edges have nothing to do with one another. They're just happen to be drawn that way in the plane. So when you're coloring, this could be red and this could be blue, or this could be red and this could be red. But of course, the coloring does go straight through. So that's how you operate the formula. You expand and you get rid of all the vertices in the graph. The reason you can get rid of all the vertices in the graph, of course, is because perfect matchings exist. Um, and so you can keep removing matching edges if you like. But you don't have to choose any particular perfect matching to do this for evaluation at 3. And the value of a loop is 3. This machinery, this little machinery, counts the number of colorings of the cubic graph. That's his theorem. Um, uh, a couple of examples here. This dumbbell is what is is not one connected. You can remove that edge in the middle and it'll fall into two pieces. Not colorable. It's not colorable because you can't color three. You can't put three distinct colors out there at the loops at the end. What happens with the Penrose formula? Well, you smooth it or you cross it, and when you smooth it, you get 3, but when you cross it, you also get 3, and that illustrates the rule for handling loops with virtual crossings. You just count them as loops and call them 3. So this is 0. On the other hand, this theta graph, as you see, gives me 3 squared for the smoothing and 3 for the crossover, and 3 squared minus 3 is 6. And indeed, there are 6 colorings of theta where you can choose 3 for the left line, then 2 for the middle line, and then 1 for the right-hand line. So that's the Penrose formula. And we want to think about this a bit. Now, did I, um, in the order that I was about to use, which is different from my slide order, I was going to say to you the one of the interesting things about the Penrose formula is that it does not work for graphs that are not planar if you tried out computing with them by drawing a picture in the plane and going through this same scanning. Um, I'm going to try to find that and show it to you immediately rather than go in the order of my slides. A dangerous enterprise. Let's see. We'll go past this and that and the other thing over to this. Here we are. So this is the famous non-planar graph K33, the gas, electricity, water problem graph. And you can check. Maybe you would like to do something while the speaker is talking. You can color it according to the rules with 12 colorings, 12 distinct colorings. On the other hand, if you applied Penrose to this picture, you would smooth it here or you would cross over. And when you smoothed it, you got a little box with ears on the sides. But when you crossed over, you see those virtual crossings don't matter. So this is just a loop on top. I mean, an edge connecting the top to the top, and another edge connecting the bottom to the bottom. You got another box with ears turned by 90 degrees, but they're the same graph. And so whatever happens in the rest of the calculation, this will give you the same result as that, and the difference is 0. So Penrose says 0, but reality says 12, and Penrose does not claim to count the number of colorings of a non-planar graph. But it gives us a nice puzzle. How can you fix this? Is there a way to fix the Penrose formula so it will count correctly for any graph drawn as an immersion in the plane? So I'll come back to that and show you one way of getting to an answer to that is to try to understand why the Penrose formula works in the first place. So we're going to use formations in the course of thinking about this. I've just drawn another one here, showing the back forth between having a formation, which is a collection of blue loops and a collection of red loops. Reds are disjoint from one another, blues are disjoint from one another. Reds and blues interact by either crossing or bouncing, and you get a coloring. And if you have a coloring, you can get one of these. So here's how Penrose defined this. He said, to each vertex with labels on it, I, j, and k, we shall associate the square root of minus 1 multiplied by epsilon I, j, k, where epsilon I, j, k is the sign of the permutation I, j, k. So epsilon 1, 2, 3 is 1, and epsilon 213 is minus 1, and epsilon 113 is 0. If it's not a permutation, if any two of the indices are equal, it's 0. So epsilon ijk is demanding that you have a coloring by 1, 2, and 3 at the vertex, and it's also placing a sign at that vertex, or a pre-sign, square root of minus 1. And then the definition of the Penrose bracket is that it is the contraction of the tensor net that you get by labeling the graph. You label the graph with indices. You have a tensor at every vertex, and you write down the tensors, one for each vertex, and take their product and regard the repetition of indices as an instruction to sum over every repeated index. And and then you get the sum over all the colorings of the graph because those are the only ones that will survive. You're taking a product, and whenever you get one of these non-permutation labelings, it gives you a 0. So the only things that survive as products are ones where they're all non-zero. So you get the sum over the colorings of G of the product over the nodes of G of plus or minus the square root of minus 1, depending on the permutation type that's sitting there. So we have to show, therefore, that this product of square roots of minus 1 is equal to 1 for every coloring, and then we will have shown that this counts the number of colorings of G. On the other hand, this formula, the Skane formula, is a tensor identity, as one can see by thinking about how epsilon tensors interact with one another. So that was his strategy, and you see that this strategy is a precursor to lots of things that we do in quantum topology and in quantum invariance, where the tensor is not an epsilon necessarily, but it might be a Yang-Baxter solution, and one is summing over the edges of the knot diagram. So it really is the case that Rogers' paper is a precursor to quantum topology. It's also a precursor to a lot of present-day method in physics, quantum computing, and other things, where people eventually realize that the idea of contracting tensors labeling some graph is a very general idea, and they call it tensor networks, and you'll find it all over the place now. It all goes back to Rogers' paper. Um, okay, so if we're going to prove this, we have to prove that this product of square roots is equal to 1. And then the formation lets you see what's going on. Now, before I do that, the previous slide is related to our initial digression. because you know the epsilon is also the defining tensor for the vector cross product. The cross product of of three-dimensional vectors A and B in the kth place is equal to the sum of epsilon ijk times the product of the corresponding entries in those vectors. You have things like A1 B2 minus B2 A1 and all that, and it's all categorized by the epsilon tensor. So the remarks I was making about getting the vector cross product into the act are actually generalized out of algebra into diagrammatics when you're looking at the Penrose count. And the fact that there is this identity about the epsilons is an interesting exercise. That's just saying that you have two epsilons tied together, which means that you sum over one of the indices, and then it breaks up into Kronecker deltas, which are the individual lines that are smoothing and crossing. I won't do the detail. But now, look at a formation. If you had a blue line that was crossing a red line, then you see that the order is the same. Red, blue, purple clockwise in the plane, and red, blue, purple clockwise in the plane. I'm taking the convention that red, blue, purple is going to give you a minus, and that red, blue, purple is going to give you a plus square root of minus 1. Okay, we have to choose. This is going to be the standard order, red, blue, purple, plus the square root of minus 1. And then if it went the other way, blue, red, purple, it would be minus the square root of minus 1. But here you get the same order. So whatever convention you chose, this will give you a pair of things whose product is minus 1. And again, whatever convention you chose, this gives you a product of things that's equal to 1 because you get red, blue, purple, but you'll get red, purple, blue here. They're opposite, and I times minus I is 1. So that means that when in the formation the curves bounce, they don't cross one another, then in the product of Penrose's definition, it contributes a 1. So therefore, the product in Penrose's definition is equal to minus 1 to the n, where n is equal to the number of crossings of these coloring curves. But these curves are Jordan curves in the plane. Remember? What do these curves look like? Excuse me. We'll go back to a picture. There are Jordan curves in the plane, and you look at one of these and you say, well, okay, blue crosses into red and crosses back. This didn't count. This didn't count. The number of crossings between these Jordan curves is 2. It's even, and so therefore it will contribute once, 1 with a plus 1, to Penrose's sum. So we've proved Penrose's formula. And we also understand now that um, why it could be that something would go wrong if you had an immersed graph in the plane, because then you might have colorings where you would have one color crossing through another color, but it wouldn't have been counted because it isn't part of this process, and then the parities would be wrong. So it could be we can therefore figure out how to correct the problem by counting such things, like this in this example. So you see, in this example of the K33, I've indicated a coloring of it, one of the colorings of it. And this blue curve, which wanders around and comes back through here, crosses through this red curve. So this is a nice coloring of it, but it's not a standard formation because of the fact that there was this immersion, and in this coloring, blue and red cross through one another at the immersion point. We ought to count that as a minus 1, and then the coloring will be corrected and will be counted rather than subtracted. So that's the answer in this form to the puzzle of how do you fix the original Penrose formula. We add a new tensor, which I've indicated by a box rather than a circle, a virtual box rather than a virtual circle. And it's given that the colors, it'll be 0 unless where's my pointer? Unless this color goes all the way through, so these two are equal, and these two are equal. But under those circumstances, if A is equal to B, it will be 1, because we don't care about that. Um, and it'll be minus 1 if A is not equal to B, since we want to count minus 1 to the number of crossings between curves in a coloring. So we add this tensor to Penrose's definition, run the definition exactly as before, and then all will be well, and it will correctly count the colorings. Now, while we're doing that, it's useful to make a kind of skein version of what that rule was. The rule being this can be thought of as the following rule: twice a fusion, which means same color is demanded, minus whatever, same or different. If you think about that for a moment, you realize that, um, for example, suppose these two colors are the same. Well, that's all right. Then fusion comes in with 2. And if these are the same, this comes in with a 1 by my definition. So we get 2 minus 1, which is 1, which is what we wanted. On the other hand, if they're different, then this will not contribute. It'll be 0, and this will contribute the minus 1 as desired. So twice fusion minus anything, ordinary crossing, um, will be a good way to say what the tensor is at the skein level. So now we have two skein relations, one for the immersion crossings for the diagram as it is first appearing in the plane, and another one that expands the edges. And between these two and the value of the loop equal to 3, the Penrose method is now fixed and will count colorings for any cubic graph drawn in the plane with immersion crossings. And so then, after some interval of time, I began to wonder about that in the sense that it's using two virtual crossings, and maybe we ought to consider seriously having more than one virtual crossing. So that's where the motivation is coming from here. So this is an example of calculating. I'm back at the K33, and I'm calculating using the box immersion crossing and keeping track of it. And I won't go through the whole thing, but I point out to you that down here in the end, I get this little class between two curves. One of them is boxed and the other isn't. And you see those two curves are contributing only a 3. They aren't contributing a 3 squared, because they have to be colored the same. And that's how it works itself out and counts correctly. Okay, so we have that. And now, where are we going to go? Well, we're going to go in a number of different directions one at a time. One is generalizing the evaluation to polynomials, um, and generalizing the multiple virtuals into knot theory. So one observation which is important here is what would happen if you just decided to generalize the Penrose evaluation to a polynomial. Now, the Penrose evaluation has been generalized to polynomials in various ways by various people. Um, this approach that I'm showing you, I think, is originally due to Scott Baldrige, who said, but you'll see what he said, all right? Just look at the calculation. We extend it this way, and with a delta instead of a 3, and calculate, just as you usually do. No extra immersion crossings. We're just back in the plane. All right? I'm keeping track of that extra immersion crossing on the slide. So, so, oh, I'm talking to the wrong slide. Sorry. I hope I had the slide that I wanted here. There it is. Good. So, One way to get a polynomial would be to decide exactly how you're calculating, and then it will be well defined. That's what I meant by originally due to Scott. Scott said, let's make a well defined polynomial by choosing a perfect matching. Once you choose a perfect matching, you can let the um, details of the scaling be any way you like. It's well defined by expanding on those specific edges. But when you do that, you can get different results depending on the choice of matching. So if you chose the matching this way, you get 2 delta squared minus 2 delta. If you chose it the other way, as in this picture, you get delta cubed minus 2 delta squared plus delta. Different. But on the other hand, they agree um, at 3. And they will agree at 3 because we're using Penrose's algorithm. But Penrose's algorithm will give different results depending on how you do the calculation if you're away from 3. There's no model underlying it other than the formal expansion. But there is a model underlying it if you choose a perfect matching, as we'll see. Okay? So, so then we're going to do the following. We're going to generalize once again into non-planar things by defining a perfect matching polynomial that is well defined for any immersed graph in the plane by having the extra tensor, the extra skein at the box crossing, and having uh, the the expansion a la Penrose at the perfect matching edge, and evaluating the loop as delta or n, where this could be integers or it could be just an algebraic variable. Well, this has a perfectly good counting interpretation. And the counting interpretation is this. You forget about trying to color the matching edges. Don't color them, just leave them as entities there that are telling you how to expand it. Color the rest of the edges, and you adopt the rule that you must have two distinct colors coming into a matching edge, and the same two colors have to leave it, but they can leave it in a different order. So you could have blue and red coming in and blue and red coming out, left to right in both cases, or you can have blue and red coming in and red and blue coming out. So that's the coloring rule. That generalizes the Penrose coloring rule. And it is generalizing the coloring rule because in the Penrose case, uh, the third color, which we could think of as red superimposed with blue, happens along the matching edge, and that red superimposed with blue is the third color. Okay, so now we have a general coloring problem for trivalent graphs with matching edges and a polynomial which is going to count that, and this will correctly count it. And the proof that it correctly counts it is basically the same as the proof I showed you for Penrose originally. Now, in back of all of this is a tautology. The tautology is that coloring locally this matching edge is the same as coloring them the same on one side and the same on the other side of the smoothing of the matching edge, or crossing them over so that you had color here and same color here, but they must be different in both cases. So I can say that if I wish to count the number of colorings of a graph, I can count the number of colorings of this object plus the number of colorings of this object, where coloring means that the wiggly line is demanding that those two circles, if they are two circles, are colored differently. And of course, if it was the same circle, the demand makes things zero. So for example, go back to the theta graph and look at how this tautology works. You expand or cross, and here you ask to color two circles in such a way that one of them is colored different from the other. And that's n times n minus 1 if you've got n colors. Here you demand to color this loop so that it's colored differently from itself, and that's empty, and so the number of them is zero. And so we conclude that the number of colorings of this theta graph with this perfect matching is n squared minus n. So you see that by thinking this way, we can forget about signs entirely. Nothing about emergence in the plane comes in, and we're simply going to be counting colorings by the time we get to the end state. We'll expand until we get to a certain collection of circles with markers that say you must be colored differently. In other words, a graph, again, all over again, a graph whose vertices are the circles and whose edges are the wiggly lines. And you're going to be looking at the chromatic count for each of these graphs. Did I make a slide of that? Yes. So you see, if I expand this way and associate a graph to each of the end states, like graph associated with two circles with a wiggly line is a line graph, and the graph associated to this guy is a loop. And then I take the chromatic evaluation of this and the chromatic evaluation of this, the chromatic polynomial of that and that. And then and then we can count colorings in that way. That's what Dan Silver was talking about in his talk. And let's go back and think about this tautology. It's a great tautology for thinking about the structure of coloring altogether. Let's go back to the three coloring situation um, and think about the famous Peterson graph. Now, the Peterson graph is usually, uh, I see how the time is going. We'll work on that, but let's stay with the graph theory for a moment. Um, the Peterson graph is usually drawn as a five-pointed star and then connected up with a nice pentagon. So the Peterson graph is two five cycles connected by some edges, and it manages to be uncolorable and non-planar. Um, and this is my favorite version of the Peterson graph. It looks a bit more like it should for a topologist, a Mobius band kind of Peterson graph. Now, suppose we apply the tautology to this. So we say, all right, we'd like to color it. We could color it in such a way that it's closed up this way and these colors are different, or it's crossover closed and these colors are different. And then you look at this and you see, like we did when we were looking at the uh, K through 3, we can pull this up and it says this little box with these two ears, the ears have to be colored differently. And then you pull the other one up and you get this little box with this upper ear and this lower ear, just a 90-degree rotated this box, and these must be colored differently. They don't cancel. We're adding up all the colorings of this and all the colorings of that. But this is a bad box. A bad box, a bad box is one where those ears will always end up being colored differently. I'm sorry. Um, Too bad. I meant to write are forced equal, of course, because that's what happens here. Try coloring this, and it forces A to be equal to B. So it will never work. And you can easily do a little side calculation on this box and check that however you three color this, and you can three color it, even though it's got a crossover in it, you can three color it, but it will, if you start with red here, it'll end up with red over there. Pardon the non-equal sign up there. I call a bad box one that forces the ends to be colored equally. And that's how Peterson ends up being uncolorable, but it also gives you a hint about what's going on with the four color theorem. Because you can make exactly the same argument in general. You can say, I have some box here and some edge out here, and then this is just a general form of some graph and an edge for that graph, and draw it in this form. And then you can say, um, if this were a minimal uncolorable graph, then when I remove this edge, I'll get colorable things and I will get boxes that will be colorable. And if they were bad boxes, I would have an uncolorable. And if it was a planar bad box, I would have a planar uncolorable. So the four color theorem is equivalent to the statement that bad boxes are non-planar. And now you can take off your mathematician's cap and put on your designer's cap or example designer cap and say, can I make a bad box that's planar? Try it, and you get some insight into what's going on here. The fact that you have three lines going horizontally from here to here is a kind of transmission cable, which makes it happen that three here, that red here will be forced to be red over there. But you have to have two transmission cables working perpendicularly to one another. This is designer talk, not proving talk, but you're trying to make one, and you see that whenever you try to make one, you get involved in that kind of thought. And of course, that may be a limitation of your thought, and there really is a counterexample somewhere, proofs on the side, but I don't think so. I think that the heuristic that the information has to be transmitted both horizontally and vertically in a bad box, and that that's very difficult or impossible to happen in the plane, is the center of the problem from my point of view. Anyway, let's go a little further. Fundamental tautology. There are two fundamental tautologies. One is the matching tautology that we just worked with, that you can smooth this in two ways and you get two coloring problems, and so you branch into all these coloring problems. The other one is Whitney's original tautology, which he called a logical identity in mathematics, which is that if you wish to color this edge in such a way that its ends are different, if you delete the edge, then they could be colored any old way, and if you contract the two ends, then they have to be colored the same. So therefore, the chromatic polynomial satisfies polynomial with respect to an edge is equal to polynomial with respect to deleted edge minus polynomial with respect to contracted edge. Well, if you go back over to the matching, you see this is an edge, and this is an edge. And you could remove it by deletion and leave it plain. You could remove this one and leave it plain, but you have to subtract two contractions. And they're the same contraction, namely that all four lines have the same value, and so you subtract twice a contraction. And now we have another solution to fixing Penrose, but this doesn't fix original Penrose. It gives us a more general skein relation that accomplishes the same result. Expand into three terms like this, and at your end states, keep track of the fact that you have to have some curves will give you the same thing because there's really a contraction going on. And there's a tensor there, and everything is working out. So that's another way to solve the problem, and it's a way of amalgamating all of the chromatic polynomials that occur at the end into one big sort of transformed chromatic polynomial, which is what this is, where these are the deletions and that's the contraction. There may be more to do with this. Now we're running out of time, so let me give you a little tour of how the multi-virtual crossings are going to happen in the knot theory. So we're going to skip some favorite graph theory about Peterson and other things, sorry, and go to virtual knot theory, which usually has one virtual crossing and a detour move. So the generalization that I'm working with here is that we're going to have many virtual crossings and they all detour over one another. So the detour move can be applied for any given virtual crossing type, and there might be lots of other virtual crossings in here. This detour can be accomplished. Each virtual crossing is free to detour over the classical crossing and all the other crossings. a very simple rule for handling multiple virtual crossings. The rest of the story is I'm going to skip trying to think about how to do it for surfaces and go to an invariant. So we would like an invariant for the case of two virtual crossings. In the case of two virtual crossings, box and circle, we really can just import what we had found in the graph theory, expand the box into a fusion vertex and a circle vertex, and evaluate just like we did chromatically. So, for example, if you had one fusion here and a standard virtual, or one fusion and a box virtual, still delta, the value of the loop. The value of the loop is chosen topologically as in the bracket. If you had two ordinary virtuals, you get delta squared. I'm not normalizing to 1 for the single loop. I'm normalizing to delta, right? But if you have a clasp like this, then you see you evaluate it and you get 2 delta minus delta squared. So that clasp is non-trivial. Now you need to see that we're really doing topology here. Actually, you needed to see it to make the knot theory work. What do you need to do to see that we're doing topology? You need to see that virtual detours still work. So if you expand, so you see the box box virtuals are expanded according to the formula, and then you expand according to the formula and check, and you see that it all pulls apart. And you have to do some similar things with the other generating basic detours. And you find that indeed detours are working correctly. And that means that when you define an invariant this way, you actually get an invariant. So this invariant has its limitations, but it is one that will distinguish quite a lot of knots that have multiple virtual crossings. And I want to spend a couple of minutes showing you what other generalizations happen and what problems occur. So the general idea, going farther than just evaluating chromatically, as it were, I call this chromatic evaluation because it comes from the chromatics idea. You could just expand the bracket. And if you expanded the bracket, you will get some entities which you probably believe are non-trivial, but you'll have to prove them to be non-trivial. In this case, we proved this to be non-trivial by doing the chromatic evaluation on it. But there could be another way, and so it goes. So you can expand down to pictures and then take the equivalence classes of those pictures up to detour moves, and then you have the problem, do I know the equivalence class? Um, so, for example, the double clasp, I know that it is a non-trivial equivalence class by calculation. And well, I can use that and some lore that I happen to know to produce a multiple virtual knot that is invisible to that generalized bracket. It's a generalization of a link. It's a generalization of links that are invisible to the Jones polynomial. Um, so, uh,
Lou, could you wrap
yeah,
up?
I know I'm running out of time, right? Um,
Okay.
Let me just do a couple of examples and we'll stop. So this is an example I was interested in calculating because of its 4D properties. It's a slice knot in that category. But we calculate it and we find that it has this in its expansion, and we want to prove that this is non-trivial. And this one is invisible. You see it's got some consecutive alternating virtuals in it. This one is non-trivial. Um, but how do you prove it's non-trivial? And um, that gave rise to thinking about generalizing quandle evaluations. You can generalize the quandle to multiple virtuals by having operators at the virtual crossings, different operators at different virtual crossings. The operators must commute with one another. Many examples of this, and you get a generalized quandle. And from the generalized quandle, you can prove various things are non-trivial. There's a lot of A lot of stuff to do with generalized quandles here. Um, and on the other hand, when you go to more virtuals, like in flat diagrams, then many things happen, but we don't know very much about them. So, for example, if you take a single component diagram with only two virtual crossings in it, it seems to reduce. But if you take a virtual diagram with three types of virtual crossings in it, certainly doesn't seem to reduce. I don't know how to prove that. So there's a strict combinatorial problem there. Um, you can generalize the arrow polynomial, but the base states will be complicated. Um, um, Myself, Sujoy, and Peter are working on a paper involving quandle and cocycle invariance, and we come upon another idea. I'm giving you a quick survey of ideas, and I'll quit. Suppose you had a diagram and you had some multiple crossings on it. You could permute them, same diagram, permute the crossings. Are they equivalent? Sometimes they are, and sometimes they're not. And sometimes it's going to be very subtle to tell. Um, and one can define the multiple virtual braid group. And this is a project of myself and Sophia in that we are proving a macro theorem using L moves, similar to the one she talked about last hour for this case. And as you see, this multiple virtual area um, contains a lot of problems, many of them analogous to problems you already know in virtual knot theory, but generalized, and some of them reaching back into the interesting texture of what goes on in the coloring combinatorics. So we'll see what happens, and I'll stop.